Okay, so in the previous video we talked about impulse, and we see that if I give you force as a function of time, integrate the respect of time between two endpoints, and they'll give me the change in momentum between these two endpoints in time, right? Over this time period. That is impulse. But what if, let's say, I do not give you force as a function of time? What if I give you instead force as a function of distance, right? So if I give you force as a function of distance, example question, right? I have a particle of mass m and expresses this force. The force depends on where the particle is located at. You see that force in this case is a function of location, right? Currently, I do not know location. I do not know x as a function of time. I do not know. I only know that the force, right, at any particular location is a over x squared. Right. So let's say, suppose I have this axis over here. This x equals to 0, and the particle starts out at some initial position. X of time t equals to 0 equals to x naught, some position here. Then, if I give it some initial speed of v naught towards the origin, right? So it moves towards the origin. It's like perhaps somebody is throwing the particle towards the origin, but as it gets closer and closer to the origin, it's going to slow down, right? The speed is going to slow down because the force is positive rightward, right? Where we define our x direction to be rightward positive. The force over here perhaps is this size, right? But the force, as you get closer and closer to the origin, x gets smaller and smaller, right? X gets smaller and smaller, and hence 1 over x squared gets bigger and bigger. So as you go towards the origin, the force gets bigger and bigger. And it's always pointing away from the origin, right? Because it was rightward positive. Now the question is, because the force is always towards the right, right? As long as we're to the right of x equals to 0, when would the particle come to a stop? If your particle is initially moving left and is being accelerated to the right, then eventually, right, the velocity is going to be 0, and we are interested in finding when this particle stops. Now, if you look at this question, right, it's actually very, very similar to electrostatics, right, where I put a charged particle at the origin and I throw another particle at it. And so this question that I've designed here is actually electrostatics question in disguise, right? It's actually a question about electric potential energy, but I'm not mentioning anything about potential energy because I want to explain the math aspect of it before we even talk about the physical aspects. So if I apply Newton's second law, it looks something like that, right? F equals ma, where f is this function a over x squared. This is actually known as a differential equation, and I'll talk about differential equations more in another video. But for now, you can think of the differential equation as a self-consistency equation. We're looking for functions x as a function of time that satisfy this. So a small digression is that when you study polynomials, right? When you study things like quadratic equations, I'm going to use a different variable because x is currently a function. So I'm going to use n, right? Let's say we have an squared plus bn plus c equals to 0. When you're given this algebraic equation, you're required to find the values of n satisfying this algebraic equation. Now, when we go to differential equations, right, we'll go to differential equations. Perhaps you're given something like minus kx equals to m d squared x over dt squared. Perhaps you're given an equation like that, and instead of finding values of x that satisfy this, you need to find functions x of t that satisfy this differential equation, meaning that when I substitute x back into this differential equation and take the derivative on the right hand side twice, right, and multiply by m, I should get minus kx. So both of these examples, right, the algebraic equation and the differential equation, they're equations of consistency, right? You're looking for solutions of n and x that make left hand side equals to right hand side. You're looking for solutions, right? The only difference is that in the quadratic equation, right, in the algebraic equation, your solution is a specific real value of n, right? But in this case, your solution is a function that satisfies these differential equations. So this is parallel, where we're basically upgrading from single values for solutions to entire functions for solutions. And there are different most of physics is about solving differential equations. It is plays a huge role in our understanding of physics. And in this case, this equation over here is just another example of a differential equation. Right? In fact, this one over here that I listed down is known as the simple harmonic motion differential equation. Yeah. So you may recognize the left hand side as Hooke's law, and the right hand side is MA. But anyway, in order to we're kind of stuck in a dilemma now, right? Because unlike the previous example where I give you f as a function of time, where you just integrate twice to get acceleration, to get the position. Now, in order to find f, right? In order to find f, you need location as a function of time. In order to find f of t, you need position as a function of time. And in order to find positions from a time, you need to find function. You need to find the force as a function of time. Right? So it's this circular dependency, and the way to resolve that is by doing a self-consistency kind of thing, where you need to find solutions to this differential equation. O stands for ordinary differential equations, compared to partial differential equations, PDE. Okay, so solving this differential equation is quite hard, and it'll be covered in future. But instead of solving this differential equation, I'm going to integrate both sides with respect to position instead of time. So if I there's a way to massage this second derivative into something that involves the derivative of velocity squared, and basically, right, by applying I'll go through the details shortly, but basically by doing that, right, you get it something like that, and this allows you to integrate the force with respect to position instead of time. And remember, of course, when we integrate with respect to position, the two endpoints must be locations, right? Must be position coordinates, right? For your definite integral, you need to integrate from one location to another location instead of from one time to another time, because now we're integrating with respect to x. And doing the integral, right, on the right hand side is integral of velocity, so you're substituting in velocity to a velocity. When we do this integral, we kind of arrive at this. And this, if you recognize this from electrostatics, this looks a lot like electric potential energy plus kinetic energy equals to electric potential energy, right? So actually, when we talk about potential energies, behind the scenes, we're actually doing this kind of math where we integrate respect to location instead of time. And that will give us the answer. I'll go through the details for the steps at the end of this video, but I just want to go through the conceptual aspects first. Okay, so the reason why I went through this example is because I wanted to motivate why we need to integrate with respect to position instead of time. And the answer is that we need to integrate with respect to position instead of time when the force is a function of position. Right? So there's no way we can integrate with respect to time without knowing x of t, which requires us to solve a differential equation, which may be difficult. Right? So for such questions, for some questions don't actually require you to know x of t in order to answer the questions. Some questions actually is enough to know the velocity, right? And in such questions, right, you can integrate the force with respect to distance, and basically with a change in variables, you end up getting that the integral of force with respect to distance is this quantity over here, right? The differences of the kinetic energies at the 2 points in time, and that is it. And this is kind of, in some sense, one way to motivate the derivation for kinetic energy, right? By considering this integral and realizing that, hey, there's a quantity over here that we are taking the difference of at these two endpoints. And because of that, it's useful to call this quantity, right, that we're taking the difference of kinetic energy. So that's just one way to motivate the definition of kinetic energy. But there are other ways, right, especially when we talk about Lagrangian mechanics. The kinetic energy can be derived from there as well, right? So the upshot of this is that the change in kinetic energy of a particle is the integral of f dx. And the integral of f dx is something we call work done on the particle. Okay? And yeah, so there's a nice parallel we see over here, which is that if I give you f as a function of time, you can calculate impulse, which tells me change in momentum. Right? If I give you f as a function of x, you can calculate work done, which tells me the change in kinetic energy. Right? There's a parallel between these two concepts. And yeah. So okay, so now we've come to the end of the video, except that since I promised, right, I'm going to go through the derivation for all this messy math. But if you are just here for the calculations, then this is the end of the video. Okay. So without further ado, since you have stayed on, let's go through the math. So we want to find acceleration. We're going to rewrite acceleration in terms of velocity. And one way we can do this is by applying the chain rule. If we take time derivative of velocity squared, right, we get 2 times the velocity times the acceleration. So in other words, this is saying d over dt of v squared is equals to 2va. Okay, and so this lets us substitute this a. We can rewrite it. We can write it on both sides, so we get something like that. Okay, substitute a back into our f equals ma, and we get something like that. So this is 2 m over 2v. This d over dt v squared, right? And we can see that we can apply a chain rule over here, because dx over dt, 1 over dx over dt is equals to dt over dx, right? And if I have a d over dt over here, then there's a chain rule. So dt over dx, d over dt, right, is equals to d over dx, which is why these two quantities over here get replaced with d over dx. So now I get this. This is just very symbolic. There's actually a lot more conceptual differences when we talk about this. Actually, we need to talk about curves in time and parametrization of curves. But these notes currently, I have not elaborated on those in these notes. So this is very symbolic, and you may be called the question, like, what are we really doing over here? And that's a valid question, and you should ask that question. And answering that question would need us to go into the definition of curve, parametrization of curve, and what it means to perform such integrals, and perhaps touch a little bit on differential forms as well. Yeah. So symbolically, we've currently managed to massage our force, right? Our force into an expression like that, the derivative of velocity squared with respect to position. And of course, since f is a function of position, right, that's great, because now we can integrate both sides with respect to position, and now the right hand side is dv squared, right? So naturally, because the integration variable, variable of integration is v squared, the two endpoints need to be v squared as well, right? And in this case, we're we're choosing to do the definite integral from the initial, right? The initial location, which is t goes to 0, to the final, where the object has stopped. Where the object has stopped, right? So in terms of position, that just corresponds to the initial position and the final stopping position, right? Because we're integrating with respect to x over here on the left hand side. And that's great because this x stop is the answer that we're looking for. So that tells us something that tells us that we are eventually going to have eventually our answer, after doing this math, we have this answer lurking inside our equation and we'll solve for it. So that's great news. On the other hand, right, initially the initial velocity is v naught. The question gives us that information. So it's some number v naught which we know. The final stopping velocity, right, by definition, is 0 because we're interested in when the velocity has stopped, right? So that's great also because if something is 0, that tells us that it's probably going to disappear from our equations. And that means that after performing this integral, we get half mv squared, right? Yeah, we get half mv squared, and we substitute into two endpoints, and we basically get kinetic energy. And so basically this left hand side in this equation 40, left hand side is basically saying the potential energy, and the right hand side is basically saying kinetic energy. We're basically saying change in potential energy is equal to change in kinetic energy, and but we're doing this in a very mathematical way. Right? I didn't even mention potential energy. In fact, for some forces, potential energy doesn't exist. So that's something that we're not mentioning in this case. We're just doing the math. We're just integrating with respect to dx. It turns out it looks a lot like EPE. It looks a lot like potential energy. And rearranging, we get the following. And we see that x naught and v naught are numbers that we know, right? So the answer is just expressing x stop in terms of the rest. So if we want to generalize this, we simply need to show that a dx is v dv, right? And if we show that a dx is v dv, then we basically generalize the above working to a more general case where we do not know the exact work done, right? But we do know that it's of this form. And the right hand side is something that we do know, we can derive, which is that it's a change in kinetic energy. So this is the derivation for the work energy theorem. And that brings us to the end to this video.